Uh, Good morning, everyone. My name is Bhanu Prasad Gollapudi, and I'm currently pursuing my PhD in Doctor of Business Administration at Westcliff University. This presentation is part of my coursework for DOC700 Doctoral Foundation under the guidance of Professor Dr. Jodi Consten. Today, I am excited to present my research on improving accuracy of CPDP models. That means cross-project defect prediction models using domain adaptation and deep learning techniques. In this current PPT, I would like to go through all these topics from introduction to references. So coming to problem context and research focuses, as you know, in current software engineering, defect prediction models help us to find fall-prone areas in code before testing even begins. So traditionally, within project defect prediction, WTP models perform well, but only when historical data from the same project is available. That uh, that's where CPDP models come into picture. It's tried to predict the defects in a new project using the data from the other projects. However, CPDP often struggles due to domain shifts like differences in programming languages, architecture, and design patterns. Because this all will change due to the target audience. So current my research focuses on improving the CPDP accuracy by integration of these three components. One is domain adaptation techniques and deep learning techniques and robust data pre-processing. Uh, Previous research highlights several challenges and opportunities. Domain shift is a major problem due to the differences in code language, style, and structure of the cross projects, and imbalanced data sets due to lead to inaccurate predictions. That means models may misclassify non-defective code as a defective codes and vice versa. So recent methods like TOMO means like TOMO means transfer learning oriented minority over sampling techniques. It's a combination of feature weighting and showed a better prediction performance in imbalanced cases. And also graph-based deep learning helps to extract the structural and relational features from the code. It improves the transferability. And also, by most models, still lack of semantic understanding of the code. So they don't compare what the code is doing, just how it was written. And also, literature gap or current limitations of a CPDP project is that many models still fail to handle the domain shifts effectively, and also many models focuses largely on the surface level features like metrics and code structure without understanding the code semantics. That means in-depth relationship between the classes and everything. And also the datasets often contains noisy or irrelevant data that impact prediction accuracy. And also advanced methods like graph embeddings and semantic aware learning are undershowed. So most models don't explain their predictions like tools like SHAP, that means shapely adaptive explanations, and LIME means local interoperable model against explanation. So these two tools are very important for forecasting the developer to trust adaptations. That means in the current existing models, these two tools are missing. So current CDPDP models, uh, these tools are not applicable. If you see the pie chart in the challenges of CPDP models, most of the CPDP models, 40% are challenges are facing using domain shift issues, and 20% are lack of semantic understanding, and 25% are class imbalances, and 15% are other limitations. So in my current research, I would like to address these issues. I'm performing the quantitative correlation study. So quantitative correlation study means where I would like to study the numerical data and data from the previous studies. And also there, I don't want to change any kind of data. I would like to explain the relationship between the variables. So that's the reason I'm going with quantitative correlation study. And this for this research, I would like to collect the data from the secondary data sources and publicly available data source like Promise, NASA, and MTP and GitHub repositories, and also previous studies. And coming to the data preparation steps, I would like to handle the missing values and encoding the category data, normalize and standardizing features, and feature selection. And if you see the right side, I explained the my current research, how I would like to take the source project and target project, how I would like to take the feature selection between the source and target project, how I explain the deep learning methods and class imbalances, pre-processing methods, and how I would like to go with the LSTM methods and deep learning methods. I explained in the clear pictorial way of block diagram. And also after once I did the data preparation methods and data cleaning and everything and applying the LSTM models and everything, I'll perform the data analysis part. So for data analysis shows that I would like to go with the statistical significance, that is p is less than 0.05. We will reject the null hypothesis and conclude that the method does improve the accuracy. And ethical concern, questions and hypothesis. How do domain in this research project? I would like to answer these two questions. The research question one is about what is the impact of domain adaptation techniques on the predictive performance and accuracy of the CPDP models, and what is the impact of pre-processing methods like data balancing and feature selection of a CPDP model accuracy. For each, I define the null and alternative hypothesis. If the data shows statistical significance, that is p is less than 0.05, we will reject the null hypothesis and conclude the data method does in fact improve the accuracy. And I'm using the secondary data sources that are well established in defect prediction researches. This include software metrics and bug reports and code module information and historical data from the prior studies, and also secondary data sources from the published research papers and experimental results, and publicly data set widely used in the defect prediction studies, including Promise repositories, NASA MDP datasets, and GitHub open repositories. And for this selection criteria, I'll go with availability relevance. I'm going with availability relevance and historical use of similar studies. Coming to the ethical consideration, ethics is extremely important, especially when dealing with large-scale datasets or proprietary code. I would like to follow these 5 key principles. One is use publicly shared, ethically sourced data, institutional review board IRB oversight if required, confidentially and anonymity of any human data, securely handling of sensitivity data, and transparent reporting and reproducibility. This ensures the research remains credible and responsible. So to conclude, my research explores how domain adaptation and deep learning can significantly improve the accuracy of CPDP models. It provides evidence that pre-processing, especially balancing and feature selection, plays a key role in production success. These findings can help software teams can catch bugs earlier, reduce testing time, and lower maintenance costs. So ultimately, it contributes a new knowledge to the uh, field of software defect and production, I'm thinking. So with practical applications in industry. Thank you. Thank you so much, team. Thank you.